Imagine this. The James Webb Space Telescope looks so far back in time that it's basically watching the universe learn how to be a universe. And then it finds something that seems too mature, too bright, too early. Welcome back to CosmoQuest 888. If you enjoy space science explained clearly without the hype, subscribe and hit like. And tell me in the comments where you stand on one big question. Do you think the universe had a true beginning, or could it be part of a much longer cycle? Webb has been spotting galaxy candidates whose light has been traveling for more than 13 billion years. In some early surveys, astronomers saw tiny red smudges that looked like they might belong to the first few 100 million years after the Big Bang. And when the first mass estimates came in, a few of these objects looked shockingly heavy, systems that on paper seemed closer to Milky Way scale than anyone expected that early. Online, they were nicknamed things like universe breakers. That label is dramatic, but it captures the feeling. If a galaxy really formed that quickly, our usual timeline needs an upgrade. Not necessarily a total rewrite, but a serious update. Now, here's the crucial caveat. In astronomy, early results often rely on photometric redshifts, distance estimates based on color. Those estimates can be fooled by dust, by older stars, or by certain emission lines that mimic extreme distance. As follow-up spectroscopy improves, some impossible galaxies may move closer in time, or turn out to be different objects altogether. But even when candidates get revised, Webb has still revealed a broader truth. The early universe was efficient. It formed stars rapidly, built structure quickly, and produced energetic sources earlier than our most conservative models predicted. To understand why that matters, picture the universe as a construction site. Right after the Big Bang, it's hot, dense, and smooth. Over time, gravity pulls slightly denser regions into clumps. Gas falls in, cools, and ignites the first stars. Those stars then assemble into the first galaxies. Our models describe this well, but the details depend on how fast cooling happens, how feedback works, and how quickly the first heavy elements appear. That's why too early is such a sensitive phrase. And that brings us to a second major pressure point in cosmology, the expansion rate of the universe, often summarized by the Hubble constant. One method uses the early universe, patterns in the cosmic microwave background, the CMB, and predicts an expansion rate around the high 60s in kilometers per second per megaparsec. Another method uses the late universe, supernovae, variable stars, and distance ladders, and often lands in the low 70s. The difference is not huge, but it's stubborn. This mismatch is what people call the Hubble tension. If the tension is real, one of two things is happening. Either we're missing a systematic error, something subtle in the measurements, or the standard cosmological model is missing a piece of physics. And that missing piece could be small, like a tweak to dark energy or neutrinos, or it could be something more radical. Once people hear radical, the big ideas arrive: bubble universes, cosmic collisions, and even the possibility that our universe is interacting with something beyond what we can observe. Now, before we go full multiverse, there's another Webb-related clue that's fascinating, even if you stay firmly inside standard cosmology: reionization. After the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen. For a while, the cosmos was filled with a kind of fog, neutral hydrogen that absorbs high-energy ultraviolet light. Then the first generations of stars and galaxies switched on like cosmic lighthouses, ionizing that hydrogen and punching bubbles of transparent space into the fog. Over time, the bubbles grew and merged, and the universe became clear for UV light to travel long distances. So here's the surprising part. Webb observed at least one very early galaxy candidate where the signal suggested strong Lyman alpha radiation. In a foggy, mostly neutral universe, Lyman alpha should get scattered and absorbed. Seeing it strongly at extremely early times implies either that the surrounding region was already unusually ionized or that the source was unusually powerful. Maybe a growing black hole at the galaxy's center. Speaking of black holes, Webb has also helped identify extremely bright early sources that could be powered by accreting black holes. And that raises a classic cosmic question. Where did the first supermassive black holes come from? If you start small, it's hard to reach 1 billion solar masses quickly. So theorists explore fast-track routes, heavier seeds, direct collapse, or periods of rapid early feeding. Here's the takeaway. None of this automatically kills the Big Bang. The Big Bang framework is supported by multiple pillars: expansion, primordial element abundances, and the CMB itself. What Webb is doing is refining the timeline, showing that the early universe may have been more efficient, more clumpy, and more surprising than the simplest versions of our models assumed. Now, if you want a truly different way of thinking, we can talk about cycles. And this is where Roger Penrose enters the story. He proposes conformal cyclic cosmology, CCC, where the universe goes through an endless sequence of aeons. Each aeon expands for an unimaginably long time until matter thins out and the universe becomes dominated by radiation and black holes. As black holes evaporate through Hawking radiation, the late universe approaches a strange mathematical limit where everything becomes nearly scale-free. So in Penrose's view, the end of one aeon can be mapped onto the beginning of the next. So where would evidence hide? Penrose and colleagues have looked in the cosmic microwave background, the faint afterglow from when the universe was about 380,000 years old. In CCC, energetic events from a previous aeon, especially the final stages of supermassive black holes, could leave subtle circular signatures in the CMB of the next aeon. These proposed signatures are sometimes nicknamed Hawking points. It's a bold claim, and the community is split. Some analyses argue they see hints. Other teams argue the patterns can appear by chance in standard cosmology. Another famous CMB mystery is the cold spot, an unusually large region that appears cooler than expected. One explanation is completely normal. A huge cosmic void along our line of sight can slightly cool the CMB. But others have wondered, speculatively, whether it could hint at something more exotic, like an imprint from a collision with another bubble universe. Webb doesn't measure the CMB directly, but it can study the distant galaxies and structure in regions of interest, helping test what's really there. At this point, you might be thinking, are we witnessing a crisis in cosmology? Not exactly. What we're seeing is a high-precision era where good enough models are being asked to be better. When instruments improve, they don't just confirm what we know, they reveal where our approximations break. And that's why the Webb story is so exciting. It connects early galaxy formation, early black hole growth, and the precise expansion history of the universe. Every time humans built a better telescope, the universe changed. Now, Webb is revealing the earliest chapters in much sharper detail, and future observatories will deepen the test. Better spectroscopy, wider surveys, and more cross-checks. The best stance today is curiosity with discipline, open to new ideas, anchored to the data. Now I want your take. Which explanation feels most plausible to you right now? Measurement error, missing physics inside our universe, or something truly radical like a cyclic cosmos? Drop a comment. Your answers decide what we cover next. And if you want a follow-up, tell me which angle you prefer: the universe breakers and early galaxies, the reionization surprise and Lyman alpha, or Penrose's CCC and the controversy around Hawking points. If you enjoyed this deep dive, subscribe to CosmoQuest 8888 and check the next video where we'll explore extreme future missions, radio telescopes on the moon's far side, probes to icy moons like Europa, and the technologies that could turn today's speculation into tomorrow's engineering. Until then, keep looking up and keep asking the hardest questions.